Hello and welcome. Tonight we're going to wander into a story about one of the strangest, quietest, and most dreamlike ideas in science: quantum mechanics. Don't worry, I'll do my best not to make it too fascinating. After all, you're here to drift, not to memorize equations. This will be a soft journey where the mysteries of atoms and light behave less like a pop quiz and more like a lullaby. So before we begin, take a moment to like the video and subscribe. But only if you genuinely enjoy these sleepy wanderings through science and history. And if you're still awake by the end, I'd love to know where in the world you're listening from and what time it is. I always enjoy imagining these quiet stories settling into different corners of the night. Now, dim the lights, maybe let a fan hum softly in the background, and let's ease into tonight's dream together. You find yourself drifting back into the 19th century, long before the word quantum entered the conversation. It was, in a way, a golden age of physics. The universe seemed neat, tidy, almost complete. Isaac Newton's laws of motion had explained the paths of planets, the fall of apples, the swing of pendulums. James Clerk Maxwell's equations had tamed electricity and magnetism into graceful formulas, showing how light itself was a wave rippling through the ether. Heat, pressure, motion, everything seemed to fit into the puzzle of classical mechanics. Many physicists at the time believed the great work was almost finished. One even suggested that the remaining mysteries were mere clouds on the horizon, soon to be explained with the same elegance as everything else. And you drift among those clouds now, floating above a world of clockwork certainty. The model of the universe was mechanical, predictable, like a great machine, every gear turning in exact rhythm. If you knew the starting positions of all the pieces, in theory you could predict the future with perfect accuracy. It was comforting, in a way, orderly. A universe that behaved politely, where nothing too peculiar lurked in the details. But of course, reality had other plans. You hover now above a laboratory, where experiments begin to whisper that things are not quite so simple. A faint glow of heat, light shining through narrow slits, the spectrum of colors emitted by hot gases. Tiny clues, tiny mismatches, like small notes out of tune in an otherwise perfect symphony. Take the ultraviolet catastrophe, for instance. According to classical physics, a hot object should emit infinite energy at high frequencies, which, as you can guess, would make life fairly unpleasant, every warm thing glowing with deadly ultraviolet rays. Fortunately, this didn't happen. But the fact that the math predicted disaster while reality remained calm was unsettling. It was a crack in the certainty. a reminder that beneath the smooth surfaces of classical theory, something stranger was waiting. Scientists still wonder how it must have felt to believe you were closing in on perfection, only to find the universe shrugging and saying, "Not quite." But that's how revolutions often begin. Not with thunder, but with whispers, with experiments that don't behave, with data that refuses to line up neatly. And so, in this calm twilight of the 19th century, physics stood on the edge of something new. No one knew it yet, of course. They thought they were finishing the story, not opening a new one. But the stage was set. The classical world, neat, orderly, predictable, was about to meet the quantum. And if you listen closely, you can almost hear the first sparks of curiosity, flickering like embers in the dark. The 19th century hums softly around you, a world of ticking clocks, iron rails, and quiet laboratories filled with brass instruments polished to a glow. In this age, light is not a mystery. Or at least, so it seems. Light, everyone agrees, is a wave. Gentle, rippling, orderly. You drift into one of those laboratories now. A narrow beam of light passes through a pair of thin slits cut into a piece of card. On the far wall, instead of two bright lines, you see a pattern of stripes, bright, dark, bright, dark, like the rhythm of waves overlapping on a pond. This is the double-slit experiment, first performed with light by Thomas Young in the early 1800s. And it shows with quiet certainty that light behaves like a wave. Not particles darting through space, not sparks flying independently, but ripples overlapping, interfering, creating patterns of brightness and shadow. You float a little closer, watching those bands appear. They're not dramatic, just soft lines on a screen. But their meaning ripples outward. Light must be a wave. It fits nicely with James Clerk Maxwell's equations, too. In the 1860s, he described light as an electromagnetic wave. Oscillating electric and magnetic fields, traveling together, moving through space like partners in a slow, endless dance. Imagine the ocean at night, the tide rising and falling in rhythm. That's how physicists of the time pictured light, smooth, continuous, predictable. And the world loved this explanation. It tied things together so neatly. Electricity, magnetism, and light were all part of the same phenomenon. A grand unification, wrapped in graceful equations. So you drift here for a moment, letting light wash over you as waves. Not blinding, not sharp, just gentle ripples passing endlessly through space. Light as a wave explains so much. Rainbows refract through drops of water. Soap bubbles shimmer with shifting colors. A prism scatters sunlight into a spectrum. These are the behaviors of waves, splitting, bending, interfering. Scientists at the time believed they were seeing the true nature of light. They spoke confidently of the ether, an invisible medium through which light waves traveled. Just as sound waves need air and water waves need water, light waves must ripple through something. The ether. It seemed so reasonable. And yet there was a soft unease. No one had ever detected this ether. Instruments searched for it, but found only silence. Light moved at a constant speed, indifferent to whether Earth was moving toward it or away. The ether, if it existed, was strangely elusive. Scientists still wonder what it felt like to believe in a medium everyone spoke of, everyone calculated with, and yet no one could find. It must have felt like chasing a mirage. But for the moment, in the calm of the 19th century, the wave theory of light held strong. The experiments agreed. The math agreed. The rainbow agreed. Light was a wave, and the universe was orderly. So let yourself rest in this version of reality for a little while. Imagine light flowing endlessly, like ripples across an invisible sea. No paradoxes, no contradictions, just the comfort of a world that can be explained with waves. The trouble, of course, is that light was not finished surprising us. Because just when everyone agreed that it was a wave, it began to behave like something else entirely. The ripple of waves fades behind you, and now you drift into a new scene, one where light refuses to stay in its lane. For all its neat wave patterns, light begins to behave like something else, something more particular. You hover above a laboratory at the dawn of the 20th century. A slab of metal gleams faintly on a workbench. A beam of ultraviolet light shines onto it, quiet and steady. You'd expect the surface to warm, maybe to glow. But what happens instead is stranger. Electrons leap off the metal. Tiny sparks, invisible except to the instruments watching closely. This was the photoelectric effect, and it did not fit with the wave story. If light were only a wave, stronger beams should push more electrons free, no matter the color. But in truth, it wasn't intensity that mattered. It was frequency. Blue light, electrons jump. Red light, no matter how bright, nothing. As though light wasn't just a continuous wave, but little packets. Quanta. Here enters Max Planck, who suggested energy comes in discrete chunks, not smooth and flowing, but portioned like coins instead of a continuous stream. He called them quanta. A radical thought meant at first only to patch a problem with radiation calculations. And then Albert Einstein took it further. In 1905, he proposed that light itself is made of these quanta, particles of energy we now call photons. Suddenly, light wasn't just a wave. It was a particle, too. Imagine the confusion. For a century, light had been a wave, elegant and proven. And yet, here it was, behaving like tiny marbles bouncing off metal. Scientists still wonder at the boldness of that step. To say, in essence, maybe light is both. Maybe it doesn't care what makes sense to us. And so, the neat world of waves cracked open. You drift now between two images. On one side, ripples of light spreading like pond waves. On the other, photons popping like sparks, striking metal one by one. Both are true. Both describe the same thing. It's unsettling, yes, but also quietly beautiful. Light refusing to be pinned down. For us tonight, it's enough to let the paradox rest. To know that in the quiet glow of a candle, in the shimmer of a star, in the flicker of your own screen, there are both waves and particles, coexisting without hurry or explanation. The story of light had split in two. And soon, it would lead deeper into strangeness than anyone expected. The lab bench fades, the photons stop popping, and you drift now into the soft glow of an idea that feels less like science and more like a riddle told by the universe itself. Light, we've learned, is both a wave and a particle. Two things at once. And if that isn't confusing enough, it turns out matter, solid, ordinary, dependable matter plays by the same rules. You hover above another experiment. This one looks almost identical to Thomas Young's old setup. A barrier with two slits, a screen on the far side. Only this time, instead of light, scientists send electrons through the slits. Electrons, the building blocks of atoms, the very stuff of matter. What should happen is obvious. Electrons are particles, so they should make two neat lines on the screen, like tiny bullets punching through. But what actually appears is an interference pattern. Light and dark bands, just like waves overlapping. Waves. Made by particles. The universe is playing a double game. You drift closer to the apparatus, watching the dots appear on the screen one by one. Each electron arrives as a particle, just a single point. And yet, when enough points build up, the pattern is undeniably wave-like. Each particle seems to know about the other paths, as if it had traveled through both slits at once. It's a quiet scandal in physics. A secret the universe kept until we asked too carefully. Scientists tried to peek. They placed detectors at the slits to watch which path each electron took. And when they looked, the interference pattern vanished. The electrons behaved like particles again, choosing one slit or the other. It's as if the universe doesn't want to be pinned down. As if observation itself changes the outcome. You hover in that space now, imagining electrons slipping silently through the slits. When you don't look, they act like waves. When you do look, they act like particles. Both stories are true, depending on how you ask the question. Scientists still wonder how to interpret this. Some say particles are waves of probability, only collapsing into certainty when measured. Others suggest parallel universes, many worlds branching with each possibility. And still others accept it as a mystery, something to live with, not solve. But for our journey tonight, the details don't matter as much as the feeling. Imagine the comfort of a universe that doesn't insist on being one thing. A universe that allows duality, overlap, contradiction. Light can be a wave. Light can be a particle. Electrons can do both. Maybe you too can be more than one thing at once. Awake and dreaming, here and already drifting. So rest with this strange duality. Let it be a lullaby, not a puzzle. The universe is telling you softly, I am not one or the other. I am both. The double slit fades behind you, the interference pattern dissolving like ripples on water. And now the story leads into something subtler. A quiet truth whispered by the quantum world. There are limits to what you can know. You drift into a study in the 1920s, papers scattered across a desk, equations scribbled in looping chalk on a blackboard. Here sits Werner Heisenberg, young, thoughtful, a little restless. He's been wrestling with particles and waves, trying to make sense of their double lives. And what he finds is not certainty, but uncertainty. His insight is simple in phrasing, though endlessly deep. You cannot know both the position and momentum of a particle exactly at the same time. If you know where it is, you lose precision on how fast it's moving. If you know how fast it's moving, you blur where it is. It's not a flaw of your instruments. It's not clumsiness in measurement. It's a built-in feature of reality. You hover near an electron now, small, flickering, elusive. You try to shine light on it to see where it is. But the act of shining light bumps it, shifts it, changes its motion. The closer you look, the more it slips away. It's like trying to pin down a shadow. The moment you think you've caught it, it moves. Scientists still wonder how best to describe this. Is the electron's location a cloud of probabilities, only collapsing when observed? Is uncertainty a hint at something deeper we haven't yet uncovered? Or is it simply the way the universe whispers enough when we try to know too much? What matters here, for our quiet story, is the feeling of it. Imagine walking at twilight, seeing a figure far ahead. You can tell how fast they're walking, but not exactly where they are in the blur of fading light. Or imagine looking at stars through mist. You can catch their glow, but their edges are fuzzy, soft, uncertain. That's the quantum world. Not broken, just unwilling to draw sharp lines. And oddly, there's a comfort in that, because the classical world demanded perfection. Every motion, every path, every orbit predictable if you only had enough information. A universe like a clock. The quantum world instead offers gentleness. It says you don't have to know everything. In fact, you can't. And that's okay. Uncertainty isn't chaos. It's rhythm. It's the universe giving things space to be more than one thing, to move without being fully measured, to exist without being fully defined. You drift in that thought now, watching clouds of probability shimmer softly in the dark. Electrons not as dots, but as waves of possibility, each one glowing faintly, overlapping, fading at the edges. There's no need to resolve them. No need to collapse them into certainty. Just let them be. And maybe tonight, as your own thoughts drift, you can take comfort in Heisenberg's principle. You don't have to pin down every detail. You don't have to know exactly where you are and where you're going all at once. It's enough to know you're here. It's enough to know you're moving. And the rest can stay uncertain. The clouds of probability fade softly behind you. And now the story drifts into one of the strangest and oddly most famous thought experiments ever told. Not because anyone ever performed it, but because it turned uncertainty into something you could picture. A box, a cat, and a question. You find yourself in a quiet study in 1935. Papers cover the desk. Chalk dust lingers in the air. Here sits Erwin Schrodinger, restless in thought. He wants to make a point about how strange quantum mechanics has become. So strange, in fact, that if you take its rules literally, you end up with a cat that is somehow alive and not alive at the same time. You drift closer as he sketches the setup. A sealed box, inside it a cat, a tiny bit of radioactive material, a detector, and a vial of poison. If the atom decays, the detector breaks the vial, the poison is released, and the cat, well, you can imagine. If the atom does not decay, the cat is unharmed. Now, at the quantum scale, that atom exists in a superposition, both decayed and not decayed until measured. And if the atom is both, then so is the detector, and the poison, and absurdly the cat, alive and dead at the same time. Schrödinger never meant this as a practical experiment. He wasn't calling for cats in boxes. He was illustrating how bizarre the quantum rules sounded when extended to everyday life. A way of saying, see, this is what our equations imply. Isn't it ridiculous? You hover now above the imagined box. Inside, the cat purrs or doesn't, stretches lazily or lies still. Both states overlap like shadows in twilight, unresolved until someone opens the lid. Scientists still debate what the cat means. Is superposition real in this way, or is it only a mathematical tool? Do things exist in multiple states until observed, Or is there some hidden layer of reality that decides for us, quietly, behind the curtain? No one knows. But the story of the cat lingers because it feels so human. We understand cats. We understand boxes. And when they mix with the strangeness of the quantum, the paradox becomes almost funny. If cats could laugh, this one might. For us tonight, though, the cat is not a problem to solve. It is a lullaby of possibility, a reminder that reality may hold more than one truth at once. So picture the box, quiet, sealed, resting on a table. Inside, the cat is alive and not alive, stretching and still, purring and silent. It is all possibilities at once, waiting. And let that soften your thoughts. Because maybe you too don't need to decide right now. You can be both awake and asleep, both here and drifting. Until morning comes, both states are allowed. Schrodinger's cat is not a trap. It's a bedtime story written in equations, whispered into imagination. And you can close the box gently now. Let it stay as it is, unresolved, and drift onward. The box and the dreaming cat fade gently into the background. And now you drift into the deeper heart of quantum strangeness, superposition. It sounds complicated, but it's simply this. Particles can exist in multiple states at once. Not one choice, not the other, but both, overlapping like chords in music or colors blending in twilight. You float into a quiet lab where physicists have set up another version of the double-slit experiment. They send single electrons, one at a time, toward the barrier. Each arrives as a dot, a particle. But together, they form a wave pattern as if each electron went through both slits at once. This is superposition. Not a trick of instruments, not an illusion, but reality at the smallest scales. You hover near one of these electrons, drifting like a faint cloud. It doesn't travel like a marble rolling across a floor. It spreads out, a smear of probability, both here and there, both left and right, until it's observed. And when measured, the overlap collapses. One position, one outcome, chosen from many possibilities. Scientists still wonder how to describe this collapse. Does it happen instantly, everywhere, as if the universe holds its breath and then decides? Or is superposition simply the truest state, and collapse only our perception catching up? The answers are debated, but the image remains. Particles like whispers of possibility, overlapping until they are touched by observation. For you, tonight, let it be a comfort. Imagine your own choices, your own paths, layered softly together like pages of a book. You don't need to read them all at once. You don't need to decide right away. You can simply drift in the overlap, knowing many futures are possible. Many notes are playing quietly together, even if you hear only one at a time. Superposition isn't chaos, it's richness. It's the universe keeping options open, humming softly in multiple keys. You drift now through a field of particles in sewer position, glowing faintly like fireflies. Each one is not here or there, but both, shimmering gently. They don't fight, they don't conflict, they simply coexist until the moment of choice. It's almost like dreaming. In a dream, you can be in two places at once, two people, two moods, without contradiction. Only when you wake does the dream collapse into a single memory. Sewer position is the universe's dream, and tonight you are welcome to share in it, to rest in the overlap, to be both present and drifting, both listening and slipping toward sleep. Because the quantum world doesn't insist on clarity, it allows quiet contradictions. It allows both, and that too is enough. The firefly-like shimmer of sewer position fades behind you, and now the story drifts into one of the most quietly astonishing features of the quantum world: entanglement. Imagine two particles, photons, perhaps born together in the same event. You watch them now, spinning off in opposite directions, glowing faintly as they drift apart. They travel far, farther still, until they are separated by miles or even light years. And yet, they remain connected. Measure one, and the other responds instantly, no matter how far away it has wandered. Their states are linked, bound by a thread invisible, a thread that space and time do not seem to cut. Einstein himself called it spooky action at a distance, not because he believed in ghosts, but because even he, careful and cautious, could not quite accept what the equations implied. How could two things, separated by such distance, behave as though they were still touching? You drift alongside the pair now. One spins upward, the other downward. One is measured, the other follows. They do not send signals. They do not whisper across the void. They simply are, together, part of the same whole. Scientists still wonder what this really means. Is information traveling faster than light, slipping past the cosmic speed limit? Or is distance itself less absolute than we thought? With entangled particles, sharing a single, extended existence, no one knows for sure. But here, floating in the quiet of this story, it feels less like a paradox and more like a promise. That connection is real, even when separated. That two things can remain bound, not by rope or chain, but by something gentler, correlation, memory, a shared origin. Entanglement isn't just theory anymore. In modern labs, it is measured, tested, even used. Entangled photons carry information in quantum computers, in secure communication experiments. Technology rests on this quiet, spooky bond. But you don't need equations or circuits tonight. It's enough to imagine the particles as companions, born together, drifting apart, yet always aware of one another, always echoing each other's states, even across silence. And perhaps you, too, have felt a version of this. A thought of someone far away, arriving unbidden. A memory shared across years. A sense of connection that distance doesn't dissolve. Entanglement is the universe's version of that. Not mystical, but real. Not imagined, but measured. And so you drift among these paired sparks, watching them move apart, glowing softly, never losing their link. They are quiet reminders that separation is not the same as disconnection, that even in the vastness, bonds remain. That distance does not always mean apart. The paired sparks of entanglement fade behind you, their quiet bond still humming in the dark. Now, you drift toward another strange gift of the quantum world, one that reshaped how we understand atoms themselves. You find yourself hovering above a model of the atom, familiar to school posters. A tiny nucleus in the middle, electrons circling like planets around a sun. It's a comforting image, neat and orderly. But as you know by now, quantum mechanics prefers riddles over neatness. Enter Niels Bohr, early in the 20th century, puzzling over why atoms emit light in such precise colors. Heated gases give off lines of color, red, green, violet, sharp fingerprints of each element. Classical physics could not explain it. Why not a smear of colors, continuous and messy? Why only these tidy, specific notes in the cosmic song? Bohr's idea was daring. Electrons don't orbit smoothly like planets. They occupy discrete energy levels, shells stacked like invisible floors around the nucleus. And when an electron shifts between these levels, it does so in a sudden leap, a quantum jump. You drift closer to an atom now. Electrons hum along in their orbits, not continuous, but fixed in layers. One absorbs energy, and without traversing the in-between, leaps upward to a higher shell. Later, it drops down again, releasing a photon, a tiny spark of light. No gradual glide, no halfway step. Just here, then there. A sudden jump, perfectly precise. Scientists still wonder how best to picture this. Is it truly a leap? Or simply the universe shifting from one stable state to another without bothering with the middle? Whatever the interpretation, the results are clear. The colors of flame, the glow of neon, the sparkle of stars, all born from electrons hopping stairs of energy. It's oddly poetic, fireworks shimmering above a festival. A sodium street lamp glowing orange, the green of auroras dancing in the night sky. Each is a choir of atoms, electrons leaping down levels, each fall releasing light. Bohr's model was not the final answer. Later, quantum mechanics refined it into wave functions and orbitals, fuzzy clouds instead of neat shells. But the idea of the jump remained, the heart of it still true. Energy is not continuous. It comes in quanta. You drift now through a quiet laboratory, watching a prism spread light into sharp lines. Each line is a story of an electron falling, a photon born, a leap across invisible stairs. There is comfort in the discreteness of it. Not everything is vague and uncertain. Some things arrive in steps, like notes on a piano. And perhaps you can let that soothe you tonight. Not everything is chaos. Some changes come in sudden, clean transitions. Here, then there. No in between. So rest in the glow of these quiet jumps. Electrons falling like raindrops, releasing photons like tiny lanterns, filling the night with color. The universe, in its quantum heart, is a staircase of light. The staircase of light fades into quiet glow. And now you drift into one of the most whispered about corners of quantum mechanics. Not another experiment, but a way of thinking about what all of this strangeness might mean. A philosophy dressed in equations, born in the city of Copenhagen. It is the 1920s. Niels Bohr sits with colleagues, papers scattered, arguments flowing late into the night. Einstein raises objections, Schrodinger sighs, Heisenberg paces. The experiments work, the predictions hold, but the meaning, that is slipperier. The Copenhagen interpretation emerges not as a law, not as proof, but as a stance. It says, particles do not have definite properties until they are observed. Until measurement happens, an electron is not here or there. It is both. It is everywhere it might be, a wave of possibilities. Only when you look does the wave collapse into a single reality. You drift now among those possibilities. Electrons shimmering like soft clouds, not yet dots, not yet decided. They hover in superposition, spread across potential paths. And then, as an observation occurs, one path sharpens. The cloud condenses. Reality chooses. To Bohr, this was not mystical, but practical. Quantum mechanics doesn't tell us what is. It tells us what we can measure. The mathematics predicts outcomes with extraordinary precision. That is enough. Asking what happens in between, Bohr suggested, might not even be a meaningful question. Einstein famously resisted. God does not play dice with the universe, he said. Bohr replied, softly but firmly, who are you to tell God what to do? The two men respected one another deeply, but here they diverged. Scientists still wonder about that argument. Did Bohr mean reality itself is fuzzy, or only our knowledge of it? Is the collapse of the wave function a real event, or simply an update in what we know? The Copenhagen interpretation doesn't settle the matter. It simply offers a way to live with it. Accept uncertainty, accept probability, accept that observation is part of the story. And perhaps that's quietly comforting. Because in daily life, you too live among possibilities. Plans not yet chosen, paths not yet walked, dreams not yet resolved. The future, like an electron cloud, is a spread of potential. And only when you step into it does one version sharpen into your story. You float now above a chalkboard, Bower's neat diagrams drawn across it. They are simple lines and waves, but they carry profound suggestion. That reality is not fixed until we meet it. And maybe tonight, as you let your breath slow, you can accept that gentleness. You don't have to define everything. You don't have to resolve every uncertainty. The universe itself, at its smallest scales, is comfortable leaving things undecided until the moment arrives. The Copenhagen interpretation whispers, "It is enough to know what you can know. The rest may stay in shadow." And so you drift onward, not with answers, but with ease. The chalkboard in Copenhagen fades, its equations dissolving into the dark. And now you drift into one of the most curious and quietly audacious ideas ever suggested about the quantum world. An idea not of collapse, but of branching. Not one reality, but many. It is the 1950s. A young physicist named Hugh Everett sits with his notes, thinking about that troublesome wave function. The cloud of possibilities quantum mechanics so elegantly describes. In the Copenhagen view, the cloud collapses when observed, leaving only one outcome. But Everett wonders, what if it never collapses at all? What if every possibility becomes real? You hover above an electron again, facing its choice of paths through the double slits. In one version, it goes left. In another, it goes right. In Everett's dream, both happen. The universe itself branches, splitting into two realities, one where the electron chose left, another where it chose right. Neither is more real. Both continue. It's dizzying, yes, but strangely, it makes the math cleaner. No need for mysterious collapse, just a wave function evolving smoothly, eternally branching. You drift now through those branches. Each split is invisible, silent. Worlds multiplying like reflections in a hall of mirrors. In one, a photon lands here. In another, there. In one, you are awake, listening. In another, perhaps, you have already drifted to sleep. Both true, both continuing. Scientists still wonder what to do with this idea. The many worlds interpretation is elegant to some, absurd to others. If true, it suggests an infinite cosmos of possibilities, a tree of realities growing endlessly with every quantum event. But for us tonight, it needn't be frightening. It can be soothing. Because in this dream, nothing is lost. Every choice is kept. Every path is taken somewhere. The universe is generous, not limited to one thread, but weaving all threads together, even if we can only follow one. Imagine standing at the shore of a river that splits into countless channels, each flowing away into the mist. You cannot see them all, cannot walk them all. But they exist, quietly, each carrying the water onward. That's the many worlds dream. You drift now among these branches, endless and silent. There is no noise, no explosion of realities, just soft unfolding, like petals opening on an infinite flower. And perhaps, as you float, you realize this, too, is a kind of lullaby. That no matter what choices you made, no matter what paths you didn't take, somewhere in the quiet branching of possibility, another version of you explored them. The many worlds interpretation does not demand belief. It simply offers an image that reality may be larger than we imagine, and kinder too. So rest in that dream. Rest in the thought of a universe spacious enough for every possibility. Rest in the quiet comfort that nothing is ever truly gone. The many branching worlds fade softly behind you, like mirrors retreating into darkness. And now you drift toward another quiet wonder of the quantum realm. Something at once impossible and inevitable. A trick the universe plays gently, without fuss. Quantum tunneling. Imagine a hill, tall and steep. In the ordinary world, if you want to cross it, you must climb over. Energy in, effort out. A marble will roll up only as far as its push allows, then roll back down. No cheating, no exceptions. But at the quantum scale, rules soften. Particles do not live as dots, but as clouds of probability smeared across space. And sometimes, without climbing, without effort, they simply appear on the other side of the hill. Not by breaking through, but by tunneling. You drift now beside a barrier, a thin wall glowing faintly. On one side, a particle hovers, uncertain. And then, without a sound, without a flash, it blinks into being on the far side. The wall remains, the rules remain, and yet the particle has crossed. It is not magic, it is probability. The particle's wave function extends across the barrier, and sometimes the universe allows what seems forbidden. Scientists still wonder how best to describe this. Is tunneling simply the mathematics of probability resolving itself? Or is it a reminder that the quantum world doesn't care for our neat categories of possible and impossible? And tunneling is not just a curiosity. It is essential. The sun itself shines because of it. In its core, protons fuse together, but classically, they don't have enough energy to overcome their electric repulsion. They should bounce apart endlessly. Yet through quantum tunneling, they slip through barriers, merge, and release light. Every sunrise on Earth is powered by tunneling. On smaller scales, tunneling gives us technologies too. The scanning tunneling microscope, capable of imaging individual atoms, and the transistors inside your phone, where electrons slip quietly through barriers as part of their work. But tonight, you needn't worry about circuits or fusion. Just linger in the image of possibility. A wall that seems impassable. A particle that simply drifts through. No explosion. No drama. Just quiet passage where none should exist. It's strangely comforting, isn't it? That even when obstacles seem absolute, the universe has its gentle exceptions. That sometimes things simply find their way through, quietly, against the odds. You float now in a soft landscape of hills and barriers, watching particles shimmer and drift, some rolling back, some tunneling through. It is not chaos. It is rhythm. A reminder that the quantum world is patient, probabilistic, endlessly inventive. And perhaps you can carry that thought with you into rest, that even when paths look blocked, there may be unseen ways through. Not by force, not by struggle, but by quiet persistence, by probability, by simply being part of a universe that allows tunnels where walls once stood. So breathe deeply. Let the barriers soften. Let the improbable feel possible and drift like a particle gently through. The tunnels fade behind you, gentle as a sigh. And now you drift into something more familiar. Because for all its strangeness, quantum mechanics is not only hidden in distant stars or theoretical debates. It hums quietly through your everyday life, so ordinary you hardly notice. You float into a modern city. Neon signs glow. Phones buzz. A hospital window glimmers faintly in the night. Behind each of these small details is quantum theory, working softly, silently. Take semiconductors, the quiet heart of every computer, every phone, every device with a screen. Their circuits rely on the behavior of electrons moving through quantum barriers, switching on and off like tiny gates. The world you know, of messages, maps, music, is written in the language of quantum mechanics. Or lasers. You drift into a laboratory where a thin red beam stretches in a perfect line across a table. Unlike ordinary light, lasers are made of photons marching in step, in perfect coherence, each one a product of controlled quantum leaps inside atoms. That tiny red dot in a classroom pointer, or the beam scanning a barcode, or the laser guiding surgery, all whispers of quantum rules. And then MRI machines, those great humming tunnels in hospitals. They see inside the human body by nudging atomic nuclei, making them align and resonate in ways only quantum mechanics can explain. You lie inside one, and though the noise is mechanical, the clarity of the image comes from the gentle dance of spins at the quantum level. Even the glow of LEDs, the flicker of your television, the clock that guides GPS satellites, all lean on quantum mechanics, steady and reliable. It's odd, isn't it? The very theory once described as unsettling, bizarre, and even absurd is now so trusted that it powers the rhythm of daily life. You may not think of it when you turn on a lamp or tap a screen, but there it is. The strange rules of electrons and photons, woven into every gesture. Scientists still wonder what this says about us, how easily we live with mysteries we don't fully understand, as long as they work. No one has solved quantum mechanics completely. Interpretations compete, paradoxes remain. And yet, you send a message, receive a photo, check the weather, all thanks to equations that quietly hold, even if their meaning is still debated. For us tonight, it's enough to notice the poetry of it, that the same principles that make electrons blur into waves also make a street lamp glow at dusk, that the same uncertainty that haunts thought experiments also steadies a GPS signal as you walk, that the same entanglement Einstein called spooky is now tested, proven, and used to send information securely across the world. You drift through the city once more, watching lights glow, screens flicker, cars hum softly. None of it looks like quantum mechanics, and yet all of it is. It's a reminder that the strangest truths don't always stay far away. Sometimes they slip quietly into your pocket, light your room, guide your path. And maybe that's comforting. The bizarre, the unsettling, the dreamlike, they don't only live in textbooks. They live here, too, in the calm, ordinary glow of daily life. So tonight, as you settle deeper into rest, imagine the quiet hum of quantum all around you. In the lights above your bed, in the circuits of your phone, in the clock that keeps time, not demanding attention, not breaking the silence, just working. Like fire once carried in bark, quantum mechanics is now carried in wires, crystals, lasers. Still fragile, still mysterious, but endlessly useful. And you simply drifting in its glow. The glow of city lights fades gently behind you, and now the story widens once again. Quantum mechanics is no longer only about electrons in circuits or photons in lasers. It reaches toward something larger, the dream of unifying all of nature's forces into one quiet framework. You drift among equations scrawled on blackboards, chalk dust floating like cosmic fog. Here are physicists with tired eyes and hopeful pens, chasing something Einstein himself never gave up on: a theory of everything. The trouble is this: Quantum mechanics describes the very small with exquisite accuracy. Galaxies of electrons, quarks, photons, all dancing to quantum rules. But for the very large stars, planets, galaxies, the universe itself, another theory reigns. Einstein's general relativity, the poetry of curved spacetime, gravity written as geometry. Both work. Both are tested, proven, precise. And yet, they don't play nicely together. Put quantum mechanics and relativity in the same room, and the math begins to snarl. Predictions explode into infinities, as though the universe itself refuses to be tied down in a single net. You drift closer to this tension. On one side, relativity, calm and elegant, explaining the bending of starlight, the orbit of planets, the slow tick of time near massive objects. On the other, quantum mechanics, restless and probabilistic, predicting the behavior of particles inside atoms and circuits. Each perfect in its domain, each whispering a different language. Scientists still wonder if a deeper truth ties them together. String theory, perhaps, with its vibrating filaments shaping particles. Or loop quantum gravity, weaving spacetime into tiny discrete loops. Or some idea not yet dreamed. For now, unification is an unfinished symphony. But even unfinished, it hums with beauty. You drift now into the heart of a black hole, or rather, into the equations that describe it. Here is where relativity and quantum mechanics clash most fiercely. Gravity compresses matter into a point. Quantum rules insist uncertainty must remain. Hawking radiation flickers at the event horizon, suggesting black holes evaporate slowly over time. But the full story, still hidden. And yet, even in this tension, there is peace. Because the questions remain open, inviting, alive. Science does not need every answer at once. It drifts like you do, slowly, softly, one possibility at a time. Perhaps that's a comfort tonight, that even the universe's deepest riddles can remain unsolved and still be beautiful. You drift outward now, watching galaxies swirl, their arcs written in gravity, while inside atoms, electrons leap in quantum steps. Two truths side by side. For all our longing to unify them, perhaps it's enough to rest in the space between. Relativity bends the stars. Quantum mechanics hums in the atoms, and you, small and quiet, drift between them at peace in both. The equations on the blackboards fade, chalk dust settling like quiet snow. You drift now into the last part of this journey. Not another experiment, not another theory, but the mood of it all. The way quantum mechanics leaves us with a universe that is not sharp-edged, but soft, probabilistic, dreamlike. Look around. The stars overhead, the atoms under your skin, the screen glowing faintly in your hand, all of it humming with quantum rules. Electrons that blur instead of orbit neatly. Photons that arrive as both waves and particles. Particles that tunnel through barriers, entangle across light years, leap between energy levels like raindrops falling down invisible stairs. It's easy to imagine this as chaos, but it isn't. It's a quiet order, a probabilistic rhythm. The quantum world isn't wild, it's just subtle. It whispers instead of shouts. You drift now among fields of probability. Clouds of potential hover around you like mist. At every moment, something could happen this way or that way. And yet, in the long run, the pattern is steady. A cosmic lullaby written in statistics. Scientists still wonder what quantum mechanics means. Is it reality itself, or just the tool we use to describe it? Are there many worlds branching with every possibility? Or is it only our perspective that collapses the wave? The arguments continue, quiet but persistent, like waves lapping against a shore. But tonight, you don't need to solve them. You don't need to collapse anything. You can rest in the uncertainty. Quantum mechanics says the universe is not fixed, not rigid, not locked. It is flexible, fluid, open. That feels like a comfort, doesn't it? That even at the deepest level, nature leaves space for possibility. You drift further into the night. The stars above you are both waves and particles. The space around you is both empty and full. The universe itself is both known and unknown. And you are both here, listening, and already drifting into sleep. Let yourself overlap like that for a while, awake and resting, aware and dreaming, superposed until morning chooses one outcome. The quantum night holds you, soft and certain in its uncertainty. Nothing is wrong, nothing is missing, everything is possible. So breathe slowly. Let the probabilities hum around you. Let the wave of sleep carry you gently inward. The quantum world is strange, yes, but also tender. And tonight, it is your lullaby. And now the journey grows still. You've drifted through the long dream of quantum mechanics, from neat classical laws to ripples of light, from particles and waves to cats in boxes, from entanglement to tunnels, from daily life to cosmic puzzles. And here at the end, all the mysteries fade into quiet. You don't need to solve them. You don't need to hold onto the equations or the debates. You don't even need to remember every strange detail. It is enough to let them drift, like stars sliding out of focus when your eyes grow heavy. Take a slow breath in. Let it settle. Let it go. Imagine the universe as a soft field of possibility, every particle humming gently, every wave overlapping like ripples in a pond. Nothing sharp, nothing rigid, only gentle probabilities, weaving together into the calm fabric of existence. You are part of that fabric. You are not separate from the quantum world. You are the quantum world. Every atom in you follows these same quiet rules. Every electron drifts in the same probabilities. Every photon of light you see is both wave and particle. And that's a comforting thought. The same mysteries that shape galaxies also hum in your breath. The same uncertainties that guide particles also guide your dreams. So let yourself soften. Let the edges blur. Let your thoughts overlap until they fade. You don't have to choose wakefulness or sleep just yet. Like Schrodinger's cat, you can be both, drifting in sewer position. Until morning comes and the wave collapses gently into rest. The night holds you, the universe hums around you, and fireflies of possibility dance just beyond thought. All is calm, all is safe, all is quiet. Close your eyes a little heavier now. The probabilities will keep. The universe will keep. And you can drift into the softest sleep.